Okay, welcome everybody. This should be an easy lesson, and I have a feeling that a lot of you already sort of know the answer to this. But to recap, we had a problem last time, and this problem came right after, right on the cusp of us solving the previous problem. So we asked the question, can we learn? And we learned yes we can learn. We can not only memorize, see data points and then know what the data points will look like in the future, but see data points and believe that we'll be able to do well on data points that we haven't even seen in the future. But we came across the second problem. This problem was machines and the way that they train give us this sort of conundrum in that when they train, right, they're searching over a list of hypotheses, and it's very likely that they will get a rare event, and this rare event will be that this hypothesis, these hypotheses that they're searching over, they returned one that happened to fall into this rare event category, which is that it misrepresents itself, that this hypothesis doesn't do well on real examples, on examples that we get outside of our sample, but it does very well in the sample. And so we get into this situation where the accuracy on the sample is really quite high, but the accuracy on things that are outside of the sample becomes quite low. And this can be, exacerbated to the point where the accuracy on your sample is 100%. You're completely right, and the accuracy when it's outside your sample is 50%. It's a coin flip. So, what do we do about this? Well, it's quite simple. We return back to the situation that we had before. And what was that situation? The situation we had before is we had one hypothesis, one sample. So with one hypothesis, one sample, we can return back to the original bootstrapping example, and we can go ahead and do bootstrap on it and get a perfectly reasonable confidence interval on how well our hypothesis that we return will do on real data. Okay. How do we do this? Very simple. When we initially take our sample, we go ahead and split our sample into two pieces that are traditionally named the training set and then the test set. Okay, so this could be a very small point in some classes, but it's an entire lesson in this class, and the reason it's an entire lesson is because it leads up to the things that we're going to be talking about later on, and it solves an incredibly important question that we've asked ourselves. Regardless, this is one of the most important parts of machine learning, and people often don't actually do this, and they often do it in an incorrect way. So let's go ahead and let's dive in. So I've gone ahead and I've added some more things to our assumptions. So we're getting quite big now. We're not done yet. So once again, we've got our unknown target function. We've got IID samples from a random variable. Otherwise, we couldn't generalize at all. We get the inputs, and then the first thing we do with our inputs is we split them into a training set and we split them into a test set. We use our training set in order to learn. And remember, learning is quite simple. The only thing that we do with learning is we look at everything in our hypothesis set and we see how well it performs on the test set. This is really quite simple when you have a finite hypothesis set, and the computer's good at it because it's able to do these very simple repetitive actions. Take a hypothesis, see how well it does on the training set. It takes the best hypothesis from the training set, called the final hypothesis G, and it compares its performance on the test set to go ahead and give us a reported hypothesis performance. Okay, this is the idea of the test set and the training set. So, as a recap, training set we use to score our hypotheses, and we will return the hypothesis with the best score. That being said, the accuracy on our training set will have nothing to do, or very little to do, and technically we can show it has a little bit to do, but it's a little bit outside the scope of the class. So for the most part, it doesn't have much to do with how well it will do in the real world. And our test set, we don't look at it at all, and we, at the end of the example, when we have our final hypothesis, we test our final hypothesis on it once. A good way to keep this in your mind is that if you're a teacher and you're teaching in class and you teach the class throughout the entire semester, one way that you could go ahead and you can test the class is you can ask them only questions that you've asked them before. In which case, it's pretty easy. You can get by with just memorizing the material, and you don't actually need to understand fundamentally the concepts that you're dealing with. But if you reserve a set of things that your students have never seen before, questions they've never seen before, and you see how well they do on these questions they've never seen before, this will give you an accurate estimation of how well these students will do in the real world. Very similar, which is kind of nice. Okay, that's it. That's kind of the entire topic. It's very important that you do this. You'll always want to do this. There's no situation where you will not want to do this, unless you would just want to be flying blind. The way that you split can be different, but I'll be covering those a little bit in the comprehension questions and later on. So let's go ahead and see an example of this. So in our example, I go ahead and I use train test split. It's pretty important. This is a function from scikit-learn model selection. You're going to use this fairly often. I go ahead and I have a test set, which is 33% of the hypothesis set, or of the sample itself. The size of your test set will depend. Again, really the only thing you care about is that you have enough data points in your test set, such that you're confident you can generate bounds around what the error will be. Okay, so let's go ahead and look at the training and test data. The way that I've generated the training and test data in this case is that I've got random variables that are being drawn. So the x variables are just random from 0 to 1. And the y variables are just random from 1 to or 0 to 1 as well. They're either 0 or 1. So in this case, you can see the x's are just completely random and the y's are either 0 or 1. So it's random. There's actually no signal in this data. It's all noise. So there's no information. The true function is just return either a 0 or 1 randomly. Okay, let's talk about the hypothesis set. This is the first time you'll see a real hypothesis set. It's pretty simple. I have 10 hypotheses. I've got one hypothesis, which is if the x value is greater than, in this case, range blah, 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 greater than 0, then we'll go ahead and we'll say it's a 1. And if it's not, we'll say it's a 0. In this case, I can try it all the way up to, so if the x value is greater than 0.1, x value is greater than 0.2, if the x value is greater than 1. So I try these 10 different hypotheses on my data. My training algorithm, pretty simple. I go ahead and I try out each of these hypotheses, and I go ahead and I see their accuracy. Let's find. So the accuracy in this case, the best one looks to be a 52, right? No, this one, 52.9, the first hypothesis in this case. So we're getting 52.9% accuracy. That's pretty bad, but it's better than random, right? So can we expect this hypothesis, the one that we trained on our training set, to go ahead and give us back a... Oh, this is shitty. Let's start this again. Hello everybody, and welcome back to Data Science Foundations. Last time we kind of ended on a cliffhanger once again. We had in previous lessons we had question on whether humans could learn at all, right? Whether we could write down a function, and this function would apply to things. Whether we could write down a hypothesis, and this hypothesis would apply to things that we hadn't seen. And we figured out that yes, we could. Today, what we're going to be talking about is the second problem we stated. When computers tried to learn, which was humans using really, really smart logic, decided a set of hypotheses for them to look over, and the computers looked over lots of hypotheses, a problem emerged. And what was this problem? The problem was the more hypotheses the computer looked at, the more likely a rare event would happen. And what was this rare event? This rare event was when a hypothesis misrepresented itself on the data. So we have a sample of data. It was a random sample. And there was a chance that each hypothesis would go ahead and misrepresent itself by being much better than it truly would be on this small sample of data. And depending on the size of the data, the chance that this hypothesis would misrepresent itself would be lower. So if it was a very, very big data set, the chance that a hypothesis could misrepresent itself would be incredibly low, because it would need to get lucky on every single data point. But if it was a very small data set that we had, the chance that a hypothesis could misrepresent itself would be very, very high. And so if we tried lots and lots of hypotheses on a very small data set, it's very likely that one of those hypotheses would misrepresent itself. Okay, what was the problem with that? Well, these hypotheses that misrepresent themselves tend to have very, very good accuracy. In which case, our computer would go ahead and return the hypothesis that misrepresented itself, this rare event happening, and we'd get a hypothesis that just wouldn't work out in the real world, but it would work on the sample that we had collected. How do we solve this? Well, it's very, very simple. We simply return back to what we were doing before. We do one hypothesis, one sample. If we're able to take a single hypothesis and test it on a single sample, then we're able to do bootstrapping and it will be representative of how it will be in the real world, assuming that this sample is, IID, it's a random sample. That's it. The way we do this is by having a test set. Now you might be curious as to why we're having an entire lesson on this. It's a little bit crazy, right? Well, the idea here is that it's foundational. This is the fundamental, is the first thing you should do as a data scientist when you get the data. You split your data into a training set and a test set. Lots of people don't do it. Lots of people do it in the wrong way. And it's incredibly important to answer what we had done before. And it will be short, so we may as well. So let's go ahead and look at our new updated assumptions. So it's the same thing. We have IID samples from X. We apply our target function to them. Again, it's unknown. We get our data set. And now there's an in-between step. We split our data into training and into testing. So the training or the testing set is used for a single purpose. We test our final hypothesis on the test set, and we're able to see a confidence interval of how well our algorithm will perform in the real world. For the training set, we use our learning algorithm. In this case, we take our hypothesis set, which is a finite number of hypotheses, and we try every single hypothesis on our train set, and we return the best one. In this case, we're able to search through hypotheses fairly effectively, and we're actually able to get a good report on how well these hypotheses will do in the real world. Okay, problem solved. Now, there are some things we need to be worried about, but we'll get to those in a bit. One way that I like to remember this type of concept is if you're a teacher and you're teaching some students and you've taught them things with questions throughout the year, and you've given them the answers to these questions, and you have a final exam. If the final exam is only the questions that you've asked them before, so it's completely verbatim, the exact same, then you can get by in the class just by memorizing. You don't need to generalize to the real world. However, if you have some questions which they've never seen before, it's a pretty good test of how well people will actually do in the real world. So if it was a math class, they could just memorize all the answers they'd seen before and not understand actually how the math was done. But if you pose new questions, they need to know exactly how the math is done. So that's one way to remember that you need to have a test set. Okay, so let's go ahead and do an example. So we've got an example in this case. I've got X data, which is random. It's from 0 to 1. And I've got Y data, which is either a 0 or 1 randomly. So I've got random data. You can't really honestly do better on this data than 50%. So that's where we are. Let's go ahead and try to train a model on this data. I'm going to be training a model, in which case I'm going to be taking a hypothesis set. My hypothesis set is 10 hypotheses, or I guess 11. My hypotheses are, first hypothesis, range 0, is that if the X value is less than 0, I go ahead and I assign a 1, and or greater than 0, I go ahead and assign a 1, and if it's less than 0, I go ahead and I assign a 0. I go ahead and I do this for each of these things, so I go from 0, 0.1, 0.2, all the way up to 1. So I have 10 hypotheses. I try each of my hypotheses, right? And I see which one is the best. That's the learning algorithm. So I had my hypothesis set, I did my machine learning algorithm, and I got a hypothesis that returned a 52.9% accuracy. How well will this hypothesis do in the real world? The answer should be, I don't know. Will it do 52.9%? Very unlikely. The idea here is that it's very likely, well, it's more likely, since we've got a very small training set, and we've got a very large hypothesis set, that we're going to be misrepresenting that we've got some hypothesis that fell into this example of having an outlier that is, hey, this hypothesis misrepresents itself. So, does it misrepresent itself? Excuse me. We can try it on a test set. This is data that it's never seen before and get an accuracy that is 0.46, so 46%. Yes, the hypothesis misrepresented itself. we can try even more hypotheses and we can see an exacerbated effect. So in this case, we get a 53% accuracy for our best hypothesis if we try 100, and it can continue on. So how do you get a correct accuracy estimate on your hypotheses? It is not by seeing what their accuracy is on the training set, but rather it's by seeing what it is on the test set. So for example, we can go ahead and we can see what the accuracy might look like under Bootstrap, and ta-da, we get something that includes 50%, which is the true accuracy of our hypothesis. Okay, recap and what's next. Okay, so hopefully this lesson has given you a lot more insight into machine learning. We've finally enough to actually talk about how machine learning is done in practice. There are some questions that I should ask you here. These are what I would call super important comprehension questions. And these would be, what would happen if I increase the size of the hypothesis set? What would happen if I increase the number of samples? And what would happen if I shift more samples from the train to the test set? So figure out what would happen in each of these examples to both the training accuracy and the test accuracy. Once you do that, go ahead, do the classic comprehension thing. Write your answers down below. If you've seen someone that has already answered this in a very similar way to you, excuse me, go ahead, just give it a thumbs up. If you write an answer that has been novel, that people haven't sort of put down before, I'll go ahead and I'll respond to it. You can do the same also with these comprehension questions. I strongly urge you to go ahead and answer these questions in your head, though. These questions are sort of foundational to, well, I'm testing on whether you understood the material that you were trained on today. So please do. If you also have some time, go ahead and answer the comprehension questions. It's going to talk a little bit about how we should test or how we should split our train and test set. And it will depend on the type of data that you have. Okay. As always, thank you for joining. Next time, we're going to be talking about some more complexities that are involved with training machine learning algorithms.